We're going to look at a few problems from the Chapter 8 assignment from the textbook. The first one we look at is number 9. Here again, this is not really there's not a lot of math in this, but what we want to talk about is what this value is right here. The standard error for the residuals is really a lot like standard deviation for normal distributions. We would say that if I were predicting for the potassium content in the cereals, then I would say when I predict, I would be off by about 30.77 milligrams from the fiber that I was predicting with, right? So we're going to plug in a value of fiber in grams, and I'm going to get out a number that's going to be my prediction for the potassium content. The standard error for the residuals is about the average amount off my prediction is going to be. So you could say my prediction would be accurate, give or take 30.77 milligrams for potassium, right? So it's just a matter of, it's the error about my line that my points would have, give or take this amount. The next one we're going to look at is number 19. This one requires me to go back and read some content in chapter 15. I'm going to just kind of summarize that as we get to that part. In this example, we are going to look at, for part A, it says, what is the correlation between size and price? I want you to notice that the way they wrote this out. The first one is price on size, and now we've got it written backwards. Now it's kind of reversed itself. Now it's size and price. When they put it first, when they reverse the order, they're asking you, would R change if I reversed it? If I switched X and Y, would it change? And the answer is it would be exactly the same. It would not be anything different than what we had previously. In order for us to find the value for R, it's going to be equal to the square root of R squared, which is no surprise. However, once we plug this in 0.714, we're going to get a value that's approximately 0.845. Now, the question is it positive or negative, right? We don't know. If you go back and look at the content, the context from problem 15, because it doesn't really have it written here, it's talking about the actual size of a house and its price. And if you read through that, it's very clear that the larger the house, the more square footage a house has, the larger the price, which would indicate they're both increasing at the same time, which would give us a positive, an R would be equal to the positive 0.845. It is very important that you take the time to justify your sign of R, basing it on either the scatter plot, the actual slope that you can see, or the content and how it's described in context of the problem. And so here we use the context because we know that it's a positive result, and so that's going to be a positive R value. In part B, there's a section in your book on page 173 that would be worth your time. It's talking about the relationship between the z-scores and our correlation coefficient R. It says that if we want to predict the z-score for Y, we would need to know the R value and the z-score for X. Notice we have a hat over the z-score for Y. This means that this is a prediction. I'm not telling you that that's exactly what the z-score would be, but we know a relationship. Obviously, the stronger R gets, the closer to the actual value we would know. But in this case, what we're going to say is that if you tell me the z-score for X and multiply times R, I can predict what I think the z-score for Y would be. In this example, they talk about the number of standard deviations away from the mean, and some of you are saying, well, I don't know where you get z-scores from, but, well, guess what? The number of standard deviations away from a mean is exactly what a z-score is. In this problem, we said that, well, if you're one standard deviation, let's see, above, if you want to predict about the price of a home one standard deviation above the average in size. So we would multiply by the z-score for 1 above, and so that would be 1 times 0.845, which is my R value. So obviously we're going to get 0.845. Would be the approximate value for the z-score for y. If I do the same thing in part C, it's asking me to do this for 2 standard deviations below the mean, or below the average for size. So we do the same thing again, except this time we're going to do 2 times the R value of 0.845, and that would get us their value for the approximate z-score. So this would be 1.69 standard deviations below the average. Now notice I said below here. This was important because this would be above. Now because I left this as a positive number, above is implied, but because this is a below situation, if I don't put negative 1.69, I'm wrong, unless I clarify that by saying the word below. You could have put a negative 1.69 there. I use the word to clarify it in that way. But if this is still a little bit confusing, there isn't any extra to know about this. It's just that if you know the z-score for x, I can multiply times r to get the z-score for y, and that's 19. Number 22. In this example, it says we have a model that's describing the roller coaster ride. It says that if we want to estimate the duration of the ride, we would say 91.033 plus 0.242 times the distance you're dropping, right? So this would assume this is in feet. We can kind of walk you through this part. Explain what the slope of the line says about how long a roller coaster ride may last in the height of the roller coaster. So we're looking at 0.242 over 1 is equal to my slope. And so this is about writing things in context of the problem. We would say for each additional foot of drop, we expect the duration to last 0.242 seconds longer. And I could add, if I didn't want to add where we say we expect, I could put the words on average at the end. Either way, I need to make sure that my reader understands that this is a prediction and it's not a guarantee, it's not a fact, it's just my estimation. Part B says the new coaster advertises the initial drop of 200 feet. How long would you predict the ride lasts? So we have our formula. We plug in 200 for the distance, and we would get up 139.433 seconds to last. In part C, we can continue with that. If another coaster with a 150-foot initial drop advertises a 2-minute ride, that would be 120 seconds. Is this longer or shorter than you would expect? By how much? What is this called? So what we need to do first is we need to figure out how long do we expect it to ride. They claim it's 2 minutes. Let's see what our formula says. Once we get it into our equation, it turns out that our prediction is 127.33. And that's obviously longer than our actual. We're going to assume that they're being honest, and it lasts 120 seconds. That's 2 minutes. And so if the question says, is this longer or shorter? Obviously, this is longer. This is the actual time is shorter than I expect. However, it says by how much? Obviously, this is 7.333 seconds longer. So 7.333 seconds longer than actual, or it's 120 seconds would be 7.33 seconds shorter than I predicted. Either way, I am overestimating the value for this, right? So what is this called? It's called overestimation, right? Our prediction is higher than the actual time. And so whenever you have, remember our residuals look like this. It's the observed minus the predicted. And so when I take that, it's 120 minus 127.33. We end up getting a negative 7.33. So whenever we have a negative residual, that means we are overestimating the value. We're over predicting the value. And that would be part C. Number 24. Here again, this is another one of those questions that doesn't require a lot of writing or a lot of math. It requires more writing. The literacy rate determines 64% of the life expectancy for a country. That is a very inaccurate statement, obviously. The R squared value is what 64% is. And R squared measures the variation. So the correct description would be that the 64% of the variation in life expectancy can be explained by the different literacy rates, right? It has nothing to do with this. Really, what's missing here is you're really talking about the variation in life expectancy, not the actual life expectancy for a country is determined simply alone by literacy rate, or at least 64% of it is. No. It's just talking about the variation. When I were going to try to predict using this kind of equation or this kind of data, 64% of the time I would have data that would fit the actual real life model. And there's going to be a lot of other things that play into this: health, socioeconomic status, just different lifestyle choices, things like that, that no one can able to predict with a little equation. In part B, it says the slope of the line measure that shows an increase of 5% in literacy will produce a 2-year improvement in life expectancy. This is a very strong statement. It's implying that you will prove, or you will always produce, a 2-year improvement in life expectancy. It's showing cause and effect. And what we know from this chapter, that correlation is not causation. You cannot show cause and effect from correlation. We can show how things change together. That things, if typically you see a higher literacy rate, you also see life expectancy increase. Now, they're not causing each other, but we know that things like this happen. Maybe it's because they have a better education system, which may lead to better health, which may lead to better health care. Who knows? There's a million different things that could potentially change here. In part B, they're trying to imply that one thing is causing it. In fact, they should have said that the slope of the line shows an increase of 5% literacy rate it wouldn't say will produce a 2-year improvement, but is associated with a 2-year improvement with life expectancy. We can say that, but we can't imply cause and effect here. All right, we're going to look at number 45 now. This is a great example of all the concepts kind of pulled together into one problem. We're going to be looking at 45 burgers. We're going to be looking at fat versus calories. And we're going to be talking about how to kind of put all these things together. First thing we're going to do is we're going to create a scatter plot. And we're going to do kind of what you would expect. We're going to base it fat versus calories. And we're just going to kind of start off. I'm looking at the minimum, right? Minimum is 19, so I'm going to start off with 20. And it goes all the way up to 43, so I'm going to just go up by 10, so 20, 30, 40, and 50. I'm leaving enough space in there to kind of get the midpoint in there, and so that would be easy enough for me to identify. On the other hand, I'm going to go from calories. We're going to start off. Calories minimum is 410, and so I think I'm going to go up by hundreds here. So starting off at 400, go 500, 600, then 700. Leaving enough space kind of in the middle to kind of gauge some of these spaces here. And this is really not for a lot of accuracy here. This is just kind of to sketch it out and put it on the paper. Okay, burgers. And so I'm just going to sketch this out. So we're going to plot that like it looks, 19, 410. So 19, 410 would be about here. And I'm just going to speed this up. And there we have it. This is our burger fat versus calories histogram. When I'm working through some of this stuff, part A was pretty straightforward. I want to make sure to include all those elements you see here: the title, the axes, the dots, all the labels and things like that. Part B asks us to do some lin-reg stuff. And so in order to gather my r-squared component, I'm going to do lin-reg in the calculator. And so we're going to say, if I look at this, we're going to get an r-squared value equal to 0.923, or you could say that's approximately 92.3%. And it says to interpret this value in context. So we'd say something like, I'm going to take into account the content here, fat versus calories. So we'd say 92.3% of the variation in calories can be explained by the variation in the amount of fat in the problem. One more time, that's 92.3% of the variation in calories can be explained by the fat content. Part C is asking us to write the line of best fit. We can get this if you run in linreg, same place you get r squared from. You're also going to generate your line of best fit, your b, your y-intercept, and your slope. I'm going to use the content, the actual variable names. So calories hat is equal to 210.954 plus 11.056 times the fat content. It's a great idea to kind of include your variable names, and when you get into FRQ things like this in the future, if I don't define my variables, now I did that up here by putting fat on the X and calories on the Y, but if I hadn't done that beforehand and just asked me to write the line of best fit, I would have needed to said X equals and Y equals off to the side somewhere. When I put it in here, I'm kind of putting that in. If I were you, I would make this a standard practice. Go ahead and put variable names in for X and Y rather than the letters X and Y, and you'll never forget to define your variables. All right, part D. So in this case, we are going to be talking about use the residual plot to explain whether your linear model is appropriate. So we're going to kind of zoom out a little bit, and I'm going to add a scatter plot onto my picture. This is the residual plot. Now, if you're not sure how to do a residual plot, you got to take that time and watch those two videos. We'll do it in class, but those videos really help to really explain things real clearly. I'm going to go ahead and I'm going to sketch this residual plot. I'm not going to put any kind of numbers on this, but I am going to put it in such a way that if I had watched it, I would have been able to tell that that someone really did kind of look at the residual plot. And so I can see here that there exists no pattern in the residual plot. We don't have really any kind of non-linear pattern happening. We don't really have a funnel-shaped picture. And so we could say that the linear model is definitely appropriate because there is no pattern in the residual plot. In the next portion, it says explain the meaning of the y-intercept of the line, right, in context of the problem, right? So our y-intercept is right here. It would say that if you had zero fat, if you did not have any fat, or if you had a fat-free item, then you would expect to have about 210.954 calories in whatever sandwich or maybe burger that you would be choosing, right? Remember, it's about choosing the X value to be 0. That would give us a y-intercept in terms of whatever calories would be expected for that to happen. Okay, the next part would be explain the meaning of slope in context. So slope here would be, if I'm going to write out slope, I'm going to go back to my line of best fit. I'm going to think about for each additional fat gram, I would expect there to be about 11.056 additional calories per sandwich. One more time, that's for each additional fat gram, we expect the amount of calories to increase by is about 11.056 on average. There's two ways you can kind of say that. And there's a lot of ways you can think about it. All right. The last part of this, G, says a new burger containing 28 grams of fat is introduced. According to this model, its residual for the calories is positive 33. How many calories does a burger have? Here's a little bit of math that we can do. Right? So we know that the observed minus the predicted is equal to the residual. Right? Now they gave us a few of these things. We know that the burger containing 28 grams of fat is introduced. So we know that the X in this problem is 28. We don't know Y yet, or the predicted Y value, but we do know the residual is a positive 33. In order for me to figure out the actual value, which is what I'm looking for right here, I'm going to have to find out my prediction. So we do that by using our line of best fit. And so I come down here, I need to know how many calories, right? So the predicted calories is going to be equal to 210.954 plus 11.056 times 28. Work all this out. Turns out that my prediction for calories is 520.522. Now, this is the predicted, right? Whatever comes out of my line of best fit is a prediction. So we don't have the observed yet, but we do know 520.522 lies there. So I know that if I subtract these two things, I'm going to get the missing piece. So I'm going to add the 520.522 to both sides, and I would get my answer. That would mean that the original observed value is equal to 553.522 calories. I just used my, this would be part G. We talked about parts E and F. I used the formula to find lines of best fit, and my formula for finding residual values in order to come up with my observed, kind of using it back and forth. So we kind of used a few. We talked about this section here. We used this section here where we actually plugged in all of the values into my formula and worked those two things out to get my solution. I hope this made sense. That's kind of a lot to go over, but it's worth spending time